Antiderivatives. We already said derivatives what? Backwards. So we're taking a function that, in a sense, we can think of as a derivative. This one is explicitly shown as a derivative. But it's not going to be always shown. Remember, this would be the answer to a problem from last semester with differentiation. But this semester, it's going to be the question. And since it's the question, even though in this example I started by showing dy dx and then having a solve for f of x is not going to stay the original function because now f of x is going to be put inside. Here's an example. F of x is going to be put inside an integral, like the x to the 3 halves that you see over there. It's going to be put inside an integral, and our job, whenever we see the integral, which technically is an elongated what? It's elongated S. Anybody remember why it's an S?
Summation.
Because of summation, because you're adding together all the areas under the curve, like the rectangles we did at the beginning of the year. It's the elongated S, but we're just going to call it an integral because no one thinks of it as an S anymore. But whenever we see that, we have to think, who's in there? X to the 3 halves. Who else is in there? Dx. But we don't have to worry about the dx when integrating. We just need to look at what function is in between. Let's go back here. What function is in between the integral and the dx? Take that function and say, hey, who is your antiderivative? We had a forever card on Friday. Who is your antiderivative? Think about who was there to begin with, but do we have to stick with, hopefully, our brains see it and we know? No. We have formulas. So I'm going to go ahead and I'm going to expand these formulas for you so that you guys can be writing down. However, do you need to write down this entire page? You could, but technically, how many of these should you already know? Well, no. The entire what side? Left side, because the differential formulas are just, what are these? Derivatives. Now, what's on the other side? Corresponding integration formulas, or integrals, we could just say. So, as you guys look at the very first one, the very first one is the constant rule. Because when we were taking the derivative of a constant, guys, what is the derivative of a constant? The derivative of a constant is 0. So question, technically, what's the integral of 0? The constant. See how we're going backwards? We're taking the 0 in the integral, going back to the constant. What constant? What did we learn about C on Friday? He's unknown. He's arbitrary, unless they tell us some other clue. He's unknown. We can say he's arbitrary. He could be anybody. The derivative of anybody is 0, so I apologize. The derivative of any constant is 0, which means that the integral of 0 could be any constant. Could it be pi? Sure. Could it be e? Sure. Could it be 1,000,000? Sure. Could it be 1? Could it be 0? Be kind of lame, but yeah. I guess the derivative of 0 is 0. Yeah.
Is k just a constant?
Yeah. But why do you think k is being written instead of c?
Because we're going to see it.
Yeah, c we're being very specific. C is a constant alone. K is a coefficient. Let me go ahead and try to zoom in just so you guys can see the right and left-hand side. Up here, this is basically just restating the whole idea of an antiderivative. You don't have to stress about it too much. Let me go ahead and zoom in. Is that better? So if we did want to label these, this one could be the constant formula of integration. Or I should say the constant rule backwards. This could be the, what is that, multiple coefficient? No. It's not called coefficient. Constant multiple, thank you. Thanks, Jason. This could be the constant multiple backwards. Because if you have an actual number besides 0 in there, it must have come from the derivative of that coefficient times x plus c. This third one, have we actually integrated? What's this equation trying to show you? Can you tell?
This is the constant out.
You can pull the constant out before integrating. which we also did with differentiation, in that we could say the constant stays, the coefficient stays, take the derivative of the function. So let me just give you guys some time in order to write these. But as you're writing them, if you're not writing down the left, look at the left and say, oh, it's that rule backwards. Take the answer, put it in an integral. And see what rules apply. Can I start slowly scrolling down? There we go. That's the bottom. If you guys notice, the last 1, 2, 3, 4, 5, 6 are all just trig backwards. But if you notice, our trick for signs, SIGNs, positives, negatives, might get just a little bit messed up with integration. Keithan's not here. Angela, who's missing diagonal from you? Who is it? Oh, Trevor. And Haley's removing from you? Okay. Just Keithan and Trevor. All right, for those of you guys in the back, let me go ahead and just put that up a little bit more. So this is the one that we talked about on Friday. This is the power rule for integration. Normal power rule, I should say differentiation power rule. N comes down, n minus 1 remains. So if we're trying to go backwards, we have to take what's given. We have to take what's given to us. I have to say, hey, we need to add a power, because 1 was taken away for your derivative. We need to add a power, but then I always think about, whenever I'm taking an integral, I always am double checking. If we just wrote x to the n plus 1, if we took the derivative, n plus 1 would come down, and if it's not there, if that number isn't chilling right there in that integral, well, we better divide by that constant, because then when this comes down for power rule, those constants will cancel. We'll subtract 1 from the power and have what remains. Can anybody figure out, while a few are still finishing the rules, why can n not equal negative 1? ¿Por qué? Yeah, the 0 would be in the denominator. That doesn't work. Oh, no. So power rule only sometimes works? Huh. We'll talk about him on the next page just for a second. There are more rules. This isn't all of them. These are the basic ones. Do you guys see, though, with the trig as you're writing them down, if you're still writing them, or just look over them one more time if you've already written them, that the signs are going to be weird? Derivative of cosine is negative sign. Integral of cosine, is going to be a positive sign. Because cosine is the derivative, positive cosine comes from a positive sign. Positive sign comes from a, well, stink, it's usually negative sign, so there must have been a negative in the cosine to begin with, because the derivative of cosine is negative sign, so that'd be a negative negative. That will work. I'll have a positive sign. All of these plus c's, plus c's, plus c's, plus c's, plus c's, plus c's are because the derivative of any constant is 0, so we're not going to see him in the integral. We have to account for him or leave space for him. But it's just going to be if there's an indefinite integral, and if they don't give us a clue, the plus c is going to be in the answer. What do you think is one of the easiest things to forget on a forever quiz or final after this point? The plus c. Kind of like the u prime was easy to forget. The plus c is even easier. Was there a question, Katrina? Did you have a question? Yeah. Okay, let me go up. The third one down.
Yeah. What words are like the names of those?
This would be the constant rule backwards. Well, okay, it depends. This one's kind of awkward because you're going to you're almost never going to see this one. Because why would there be a 0 in? This one you could call the constant rule for integration because it's integral of a constant. This could be the constant multiple rule for integration because there's a coefficient of the function that we can pull out. Sum and difference rule for integration, how you can split up integrals and take them one function at a time. So these two are just saying like how integrals behave, kind of. You can pull coefficients out and you can split up addition, subtraction. What don't you see? I don't see f times g. I don't see products, and I don't see f divided by g. I don't see quotients. Stink. Then it'd be power rule. Then it would be, it's up to you with these ones. It's the sine rule backwards or it's the cosine integration. Is that cool?
Yeah.
Up to the very first one? There you go. Other years I handed out, but this year I just had you guys write down. You're not going to like it, kiddos, but this entire thing, I'm zooming out. I'm getting myself a yellow box. You're not going to write the entire chart, just this side. Just this side. You don't have to put names unless you want to. You don't have to put names unless you want to. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You could do, that's awkward, sorry. You could do 5 and 6. You could do 4 and 4 and 3. I don't know. It's okay though, you can fit it in. But what's it called? Basic rules of integration. Does that sound good? Or basic integral formulas, either way. And this is our forever number 31. Okay, forever number 31. I need to update your forever cards online, but you guys have them written in your notes. I apologize. I'll get them online. Probably tomorrow. Today I have a meeting at lunch. Okay. This was just me making it big, and I forgot I made it big, but there they are big. Okay. Before we go on, let's talk about that power rule one real quick. The power rule. The one time the power rule doesn't work is if n is equal to -1. So let's look at that example real fast. Why doesn't it work? Okay, we know the rule doesn't work. We're dividing by 0, but why wouldn't it work? What would it look like? If I had x to the -1, if we look at it this way, it's not going to really mean much. But if we think about it in other terms, how can we rewrite something with a negative exponent? Ooh. So we could make this the integral of 1 over x. And if inside an integral we're saying, hey, you were the derivative of somebody, why does power rule not work? Because there is no x to a power that has a derivative of 1 over x. The only function that has a derivative of 1 over x is ln. Why does this get tricky? Because it looks like a power rule, but what would happen if you tried to do the power rule? You would have x to the -1 plus 1, x to the 0 over -1 plus 1, 0? So the nice thing is power rule breaks down for this example, which is a good thing because the answer to, or the integral of 1 over x dx, his antiderivative is ln of, now here's where it gets a little funny. We're going to have to say ln of absolute value of x. And part of that is because of, remember your card matching thing? Some of you guys got confused because ln of x's derivative is 1 over x, and you were looking for the basic graph 1 over x, and what wasn't in your cards? Why wasn't it there? Yeah, you can't have a negative in a normal ln, and so 1 over x was restricted and cut down to just this one branch or this one portion. But hold on, are we starting with ln or are we starting with 1 over x in an integral? What are we starting with? We're starting with 1 over x. So what's 1 over x's domain? All real numbers. So we have to make sure that ln, well, all real numbers but 0. But we have to make sure that ln also is allowed for all numbers positive and negative, hence why we have the absolute value. Does that kind of make sense? The reason is ln is restricted, 1 over x is not. So if we start with 1 over x, then we have to make sure ln is not restricted either. Except at 0, which is fine. 0 doesn't work for him, 0 doesn't work for him, perfect. That matches up. Let's take a few more notes before we get to the let's just get practicing. Ooh, we're close. It's right there. Okay. One more page of notes. And this was the one that, wasn't going to work out so well on Friday with me still hobbling on those crutches. But with my cool scooter thing that Katrina and her mom let me borrow. We got this. This has to do with the plus C. Family of antiderivatives. We're just kind of talking for a couple more seconds about the plus C. We've already talked about the general idea as to why the plus C is important, is needed, is necessary. What would you have blank actually? That's weird. Shh, no judgment. Come on, you're jealous. At least pressure. That doesn't work, because integral constant of integration, that's like double stating. We don't want to be redundant. How about integral? Oh, I know what I'm saying. I'm describing an indefinite integral. I'm not naming the plus C. We already talked about him. He's the arbitrary constant. Integral without bounds, that's an indefinite integral. Versus, I'm not going to leave it up here because we're not learning about this type quite yet, but versus an integral with bounds, which would be with an actual number here, I'll call it A, and a number here. Some of you guys who have looked at calculus problems, you might have seen numbers and integrals before of a function. This is a specific area for a specific region. This is the one your calculator can do. The indefinite is the one your calculator can't do. This one should equal a number as long as there are numbers plugged into the constants. This one equals an equation. Anyway, we'll talk more about the differences once we talk about definite. But here's the idea. If we were to take, what's a good example? If we were to take the example of 1/3, no, we don't want that. Let's do 3, let's just do 2x. Okay, if I take the integral of 2x. As you're looking at that problem, you see the 2x, you zoom in on that function in between the integral and the dx, sandwiched between the integral and the dx, you say, hey, where did you come from? Now, if we were to use the power rule for integration, you have your table, right? If we were to use the power rule, technically what would we do to solve this? Don't jump to the answer. We would pull out the 2, because we can. It's a coefficient. We would pull out the 2, and we would leave the x, and we would see him to the first power dx. This is just rewriting. We would go ahead and then keep the 2, integrate the x, and make it x to the 1 plus 1, all over 1 plus 1 plus c. That's technically the power rule for integration. I'm doing this the long way. And what do we end up with? What's 1 plus 1? Nice. 2x squared all over 2 plus c. What's my final answer? Now, how many of you guys saw that before I went through the whole crazy process? Integral of x squared is 2x. Derivative of x squared is 2x. I have to retrain my brain. Integral of 2x is x squared plus c. But what does this actually turn into? Why am I saying that the answer to an indefinite integral always represents a family?
Because any number.
So how many solutions are there, first of all? Infinitely many, but they are related. Family, see? Relations, you guys saw a lot at Christmas. Right? They're related, but how are they related? What are they off by from each other? Addition on the outside. What kind of transformation of the graph is that? Ooh, it's a shift, right? So technically, how could I show the family of antiderivatives? I could say, oh, hey, there's x squared plus 0. Hey, there's x squared plus 1. Hey, there's x squared plus 2. Hey, there's x squared. I can keep on going down here, right? x squared minus 1, x squared minus 2. Okay, that's approximate. But it's a family of antiderivative. There's infinitely many, and they're all related. They're just vertical shifts of each other. And that's why I said if they give you a particular point, that's going to limit you to which particular function they're talking about. But in order to be able to limit it to one answer instead of the infinitely many, you're going to have to be given some sort of x, y, which you could use to go ahead and plug in. There's the x, this is all equal to y, and find the c. Then you would have your one specific. But if they don't give you a particular condition, you're stuck with the family of antiderivatives. And that's why the note at the bottom says you can only find c when given a point. You can only find c if they've given you some sort of clue about the original. Otherwise, you're kind of stuck. But that's okay, that's on purpose. And then down here at the very bottom, all I'm trying to show you is if you do take an integral, look on the inside, if you do take an integral, you're going to get a function. You can always double check by deriving to make sure it matches the original in the integral. Does that make sense? You can always double check by deriving what answer you think should be the solution to the integration formula. The answer you think it is, you can always take a derivative. Sometimes you can mentally do it and be like, oh, I did something wrong. Hold on, I need to adjust. Something's wrong, something's off. Maybe I forgot a constant. But in order to be able to double check appropriately, don't you have to know your derivative rules really well? So for instance, if I had candy, but I haven't because obviously I'm not going to the store very much right now. But pretend I have candy. What? Dum-dum quiz. What's the derivative of sine? Positive? What's the derivative of secant? No, it's positive, you're right. Secant tangent. What's the integral of secant tangent? Secant. You have to be able to go backwards. Ah! What's the derivative of tangent? So what's the integral of secant squared? Who's not saying plus c? Ah! What's the derivative of cosecant? Negative cosecant cotangent. So what's the integral of cosecant cotangent? Negative cosecant plus c. Ah! What's the derivative of cotangent? Negative cosecant squared. That's, wait, derivative. Only for. So what's the integral of cosecant squared? Negative cotangent plus c. What's the integral of sine? Negative cosine. We gotta train our brains. And if you're not saying it right now, that's okay. We haven't even had a forever quiz. You just wrote them down. But we need to train our brains with those signs and going backwards. Christian?
So whenever you integrate, you always have to put a plus c.
Yeah.
No matter what.
Yeah, as long as the integral has no bounds, has no little numbers written, there will always be a plus c. But sometimes if they give you a clue, we might be able to get rid of that plus c and then not, like in a following step. But you always start with the plus c. Okay, so what if I was to give you something like, I'm going to only show one at a time, or some of you who are a little bit quicker than others are going to be like, ha ha ha, I finished them all. Okay. Write it first. Identify for me. Some of you can go, that's fine. Go, just don't annoy the people around you by showing them, haha, I got it. What are two rules that we should use with this integral? We can take out the 3, the constant multiple, and we can also use the power rule. Now, hopefully we'll get fast at these just like we did with the others. But for right now, I'll show all the steps, yeah? So I'm going to show one at a time. Most of you aren't going to need to keep writing the step of pulling the 3 out, but we can if it's confusing to you. Now we have an x to the n. Some of you need to go look at that table and remind yourself of the power rule. What do I do with an x to the n? We say Hey, the derivative took away 1, so we need to do what to his power? Plus 1. Is it okay if I just go to 15? Now hold on, think through with me. I'm going to do a division, but why? If I have 3x to the 15, if I'm taking the derivative of this guy, what's going to come down? The 15. Who's not here? A 15. So I'm just going to go ahead to make things easy. The 3 is still chilling. He's the constant in front. I have x to the 15 over 15. Now check it. Bring down the 15. Boom. Subtract 1, 14. Haha. I got it. But what do I need? A plus c. Now, let's not leave it like this, right? We ultimately have 3 over 15. What does that end up being? 1 over 5. Someone help Brendan out real quick. 1/5 x to the 15 plus c. Now, how can, and this is the great thing about integrals, because it's going to be annoying training your brain to go backwards, but what can you do with any answer that you think you have to an integral? Derive it. Bring down the 15. What's 15 over 5?
3.
Subtract 1. Did I get it? Yes. Why? 3x to the 14 is the derivative. Dun, 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 dun. Does that make sense how your derivative skills are going to help you double check real fast for some, if they're right? Ready? Set? First, any quick questions? Go. Do another one. All right, hold on. Let me not totally cut you loose yet. Go ahead and write it down. Do you remember with deriving how we rewrote to make things easier? Okay. We can rewrite, exactly. And why did you say 1/2, Katrina? The square root. So I can think of it as x to the 1/2, which means I'm using the power rule. But why am I putting a dx right here and putting a big old minus with an integral? What other rule am I using? Yeah, the sum and difference rule. I can take these one piece at a time. Technically, the 3 doesn't have to stress me out. He can just come out, and I'll deal with him in a second. And I'm going to have to use the integral of sine rule, right? How are we doing with the rewrite? I'll give you a couple seconds to try to use the rules on your own. The 1/2 does throw a kink, but it kind of did with deriving too. We had to learn what to do. With fractions, remember how we thought of 1/2 adding 1 is adding 2 over 2? Sorry, subtracting. We were doing derivatives. We thought of subtracting 1 or subtracting 2 over 2. We can do the same thing with integrating. We can add 1 by adding 2 over 2. I'm going to show the work just to make sure we're okay. I'm adding 1 like the power rule tells me. What else do I need to do for my power rule? Not yet. Divide by n plus 1, right? Now, we could do, because some of you are like, oh, plus c. Okay, you're right. You're right. I'm going to go ahead and do plus, if this is okay, just to get us used to what I'm about to show you. Let's do plus c1. How come? Do you guys notice how many c's we're going to get? Yeah, we're going to get 2 of them. We'll talk about how to make this a little bit easier in just a second, but for right now, all right, we have plus c1. We have a c. I don't know why I just put that dot there. Okay, coming back. Overkill. It's like using Clorox while you need to do a study. Okay, so over here, now we have minus 3 times, who already looked at the rule or remembered it? What's the integral of sine? Ooh, negative cosine. That's snazzy. Plus his own little c, let's call him c what? Sure, why not? Now how do we rewrite this to make this prettier? Who's already figured out what 1/2 plus 2 over 2 is? 3/2. Now we could divide by, remember it's the exact same addition. We could divide by 3/2, but ew, that's gross. Can we multiply by the reciprocal? Here's a cool trick with any fractional power. You add 1, figure out that power, multiply by the reciprocal. Because look, when I bring down 3/2, what's going to happen if 2/3 is waiting? He's gone, which makes sense because he wasn't here in the integral. Now, I'm going to leave off this C1 for a second because he's a constant and we can rearrange addition. I'm going to move him to the end. What's a negative times a negative? So we have plus 3 cosine x. And here's where it gets snazzy. Every time we do integrals of separate pieces, we can't go ahead and we can show like a C1 and a C2, or say there were 3 pieces, a C3. Or we could just say, you know what, hold on. What kind of problem was it to begin with? A single integral, right? And a single integral would have a single plus c, right? So we could say, hey, plus some arbitrary constant plus another arbitrary constant can combine to be a third arbitrary constant, and we could call him a constant plus a constant is a constant. That's what I want you to think about. So C1 plus C2 is C3, but we could just say, whatever, it's arbitrary. Let's just call him C. So we don't actually need to write all these different plus C's when we're just splitting it up to make it easier on our brains. It's just going to end up with a plus C at the end. Now remember, it's one of the easiest things to forget. But you don't necessarily need to be writing all these plus C's as you're trying to just solve the basic integrals. Now, how do we double check again? Take a derivative. So bring down the 3/2. What happens? Subtract 1. Or subtract 2 over 2. And do we get x to the 1/2 alone? Yes. Which is the square root of x? Perfect. What's the derivative of 3 cosine? Negative 3 sine. What's the derivative of a constant? 0. Dun 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 dun. Is it making sense? But do you see how we just kind of need to practice to get better and faster? Ooh! What's going on with this guy? But we don't have a quotient rule. When we took derivatives, we didn't used to have a quotient rule either. And before the quotient rule, we realized sometimes rewriting made the difference. Not as in subtraction, but there is subtraction, it works. How can we rewrite this problem to not have division, since we don't have a division rule? That's one way. That's one way. We could see this as 3x squared minus 2 all times x to the negative 2. Do you guys see where Katrina got that? This is in the denominator. We can make it x to the negative 2, and that's what brings it up. And what are we going to do? Distribute. But what's another way that we could have done this? You're allowed to break up when there's addition or subtraction on the top. When I taught Algebra 1, I called it the heart method. You can go ahead and group this guy with the denominator because he has that denominator, but this guy also has that denominator. I have 2 separate pieces with a common denominator. It's a silly way of remembering it. I call it the heart method, but basically you could also think of it as, and they both end up in the same place. You could think of it as 3x squared all over x squared minus 2 over x squared dx. I'm not killing anything, because I'm saying, hey, this got put together from 2 guys with a common denominator. So I'm just separating it. I'm taking them apart. But look at what happens with either one. Where do we end up with in order to be able to keep taking the derivative? At the integral of, it's much more essy than I wanted. At an integral of, what do I do with x squared times x to the negative 2 when I add the powers? X goes poof. X to the 0 is 1. What happens here? The x's cancel. I just get a 3 minus 2x to the negative 2. Let me give you guys a second, or should I say a whole minute, maybe 2. Can you guys finish? There's a rule for a constant, k, alone, and there's a rule for a coefficient times x to the n. Let's see what you get. If you want to, you can look at the table. Look at the integral of k dx. It's the second formula. And look at the power rule. It's the 4th or 5th. Someone help Trent and Brandon out. If they have answers, just check them and see if it makes sense, but otherwise. Hang in there, guys. I know it's warm. I'm not going to solve it. I'm just splitting it up so that we can see our pieces real quick. If you like rewriting, this might help you fit it to the rules if you're a little overwhelmed. Who figured out what to do with the integral of a k, not a 0, a k dx? You add an x. Why? Oh, because the derivative of a number times x is just the number, is just the coefficient, right? Derivative of 3x is 3. Oh, that makes sense. Could I write a plus c? Yes, or I could just write a plus c at the end and say I know that his c and his c combines to be a new c. Now, this power isn't -1. I can use the power rule. It's going to work out. I'm going to have x to the, let's see if we can train our brains. What's -2 plus 1? We want to add 1. -1. And once I get that number, what am I dividing by? -1. That way, when the -1 comes down, that's waiting for him. Now, let's just simplify. I end up with 3x. What's a negative divided by a negative? Positive. I could write it as 2x to the -1 plus c, and is that right? But why am I going to do an or? Yeah, I can also make the x to the -1 a 1 over. There is a 2, so I'm just going to go ahead and put a 2 over x. But hold on. Stink. Why am I going to do another or? If I can get my or. Wasn't it all one nice fraction to begin with? So couldn't I also need to get a common denominator? Remember, make it match. What did I do? I multiplied by x over x. Make it match. It depends on what's in the back of the book. But was this right? Yes. Was that second one right? Yes. Was the third one right? Yes. Dun 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 dun. What are you supposed to do tonight? Start your homework. Why? Because we're competing tomorrow. And you want to at least have a little bit of practice, you yourself, at the speed that you want to go, however slow, in order to work on it. Guys, I'll be here today after school. Tomorrow I'm doing basketball games, maybe, if they let me. We'll see. Otherwise, see you guys later. Bye. Chapel day. Imaginary bell went beep. Thanks, guys, for hanging in there.
Huh?